16, getting ready for the 14th problem. So a little bit more than halfway through these problems, getting more difficult, but also still lots of fun. Let's see what we've got tonight. One-time pad. Run out of keys, okay. MD5 of a prearranged salt. Okay. Increasing integer. Okay, got it. 64. Okay. Got it. Do I still have my MD5? Yes. That's good. Okay. What I might need is key. 3 of the same character in a row, so hash is key if, let's see. Only consider one of the next 1,000 hashes contains the same character 5 times in a row. Okay, so maybe like next 1,000, like this. Let char be, so we can take and then filter on I equal, and then get like the first of the first of this, and if let, and then we want to say it has to be the case that sum in the next 1,000 of these hashes matches I think the Java way to do this is there's a compile pattern, might be a closure regex re p compile. No, let's take a look. re for the regular expression builders. Re pattern, pretty good. So re pattern of stir dot star, begins with dot star, ends in dot star, and then in the middle, repeat 5 of this character like this. Okay. What index produces your 64th one-time pad? Right. So let's see. Def salt ABC sequence. All right. Salt starting with 0. So map stir repeat salt to range. Map 5 to this. Now I have to set up this is key here. So I think I could use a partition 1001 like this. Is this right? So I think maybe more like that. Then filter. Let's see. All right, I'm going to make this into all right. So for input input in this, let the index range, let the hash. Maybe, okay, I think I can do this. Map indexed, a function from index and a string that returns index and MD5 of the string. Okay, then this looks good. And is key, let's see, yep, that's fine. Then the structure in here is going to be is key. So the input is going to be 1,000 things. The first thing here is going to be a structure with index and then hash. And then the rest of these I can just map second to them. Okay. Wrong number of args passed to is key. It is key, an anonymous function in here. All right, that looks good. Right in here, I want to say like that. String can't be cast to a pattern. Right, so this is so I can call RE pattern on this thing. Illegal escape sequence. So really, oh, there, like that. That. Okay. Filter is key. Get the first thing out. Right, and then let's key sequence. Get into this namespace. What? I misspelled sequence. Okay. Okay, apparently is key is returning. Let's see. I want just the like this. And this thing here. It says 39. First index, because the MD5 ABC 18 contains this. The next index, eventually this index meets all of the criteria. All right, so I'm, nope, okay, oh, hang on a second. Filter is key. Take 64 of these. Find out what the last one of these is. Apparently it's kind of expensive to compute, so maybe we can redefine our salt and run it in a different, run it in this REPL here. Okay, 23728. So this looks correct. That's a pretty solid result, I would say. So yeah, we just have to wait for it to finish. Okay, 19626. Not the right answer. It's too high, it says. Okay. All right, yeah, I think. Well, it seemed to give the right answer for, maybe because I wasn't redefining. No. Did it give the right answer here? This is a pretty big data structure. Maybe I'm pulling my answer out in the wrong way. All right. So map indexed, make these into this thing. Filter is key. Maybe what I should do is I should just do like a keep here and say if this is the index, then we say like if there's any of these, then return the index like this. So, okay. Yeah, I think that what I was doing is I was looking at the wrong number. See how these numbers are all going up? Yeah, I think this is the answer. 17, pretty good. All right, next step. Even more secure, key stretching. Don't know what that is. Spend more time generating hashes. Unfortunately, okay. To implement you first, whenever you generate a hash, before you use it, first find the hash of that hash and then the hash of that hash for a total of 2016 additional hashings. Always use lowercase. For example, to find the stretched hash, find the MD5 of ABC0. Okay, so the stretched hash of index 0 in that situation. Yeah, okay. In the end, you find the original hash, then find the hash of the previous hash 2016 times for a total of 2017 uses. Got it. The rest of the process remains the same, but the keys are entirely different. Okay, so okay, so let's, instead of MD5, let's MD5 2016. And then I'm also going to have to think, so this is going to be the nth S. Iterate on MD5, starting with S, take the nth. Let's see, the first one is going to be S. Second one is going to be running it once, which means if we're running it 220 here like this. Okay. Let's just verify that we're doing this right here. Of ABC0. And then we find 2B. So the stretched hash, find the hash of the previous hash. So the stretched hash is, okay, that's not right. Am I doing this wrong? CFC. Oh, I think the issue is, yeah, lowercase. So in this situation, to lower case. E10. Okay, got it. So MD5 2016 looks good. Then, I guess, kick this off. Nothing else has changed, correct? Yeah. All right, I'll kick it off here and think of a better way to do this. Let's see. Yeah, it's definitely a lot of hashes. If most of the time is being spent computing hashes, then I just made my program 2,000 times slower. I could try to utilize more CPUs. Let's see. I wonder if there's some structure I can exploit here. Once I hash something once, then it gets to be pretty random. And I'm not aware of anything in MD5 that would help me out here. I guess I could separately test the salt APC just to make sure that I'm not going to be wasting a ton of time. So let me paste in a little bit of code here. So take ABC, and then now I only want the first one of these. And let's see. This seems like a very reasonable time investment because I definitely want to make sure that my is_key code is returning the right thing. Well, I do have. Let's see. I do have AVPS doing something completely unrelated to. So the answer here that it gives is 10. Second triple E. Okay, index 10. Okay, all right. So that gives that anyway. That didn't seem to take too long to compute. That seemed like it only took. Maybe like 10 seconds. So if it takes 10 seconds for the first one, then it should only take 640 seconds for the next one. It'll be quite a challenge, I think, to like make a distributed, parallelized program in faster than I'm estimating this is going to take. It would be nice, of course, if we could dig into the state of the program. It would also be nice if, we had better, we had written the program in a way that was going to be, more efficient somehow. But I think our best bet is going to be waiting on this. I guess something that we can do is, so let's see, do I need anything special in my REPL here? So I think I have a little Inky project, and I'm going to have to establish a local, so that I can connect through NREPL. I have to connect to, nope, this. So I need an SSH tunnel. So let's see. So connect to REPL, this one. All right, and then what we can do is we can put something in here like found a key, and let's see, run this and like run this in the remote REPL here, and then I think, hang on a sec, this should be that. Yeah, run it. Couldn't locate Instaparse. Okay, well, we don't need Instaparse. Oh, no, it's looking for my, it's looking for this clipboard stuff here. What if I take this out? Still try to run. Okay, it looks like it is running the code, and in this REPL here, it should report when one of these keys is found to match. Let's see, am I repeating any work? I don't think so. I think that because we're using this map indexed here, we're only taking, so hopefully the case that it was trying to sort of catch us on was that we were like computing MD5s Okay, that seemed like it took about okay. All right, so it's finding them. I don't know. Unfortunately, I can't really join this process of computing right here. Um, so I don't know, where it is, or how far along it's gotten, or the numbers that it's looking at. Let's see. Is there another way? Is there another way to do this? So you do have to compute. I'm pretty sure you do have to compute all the MD5s, because otherwise, how would you know whether there was a subsequence? But maybe once, maybe that would be, maybe a better way to do it would be to like compute all the stretched keys, and then like just you could distribute them among computers. But yeah, this has only been running for about 2 minutes or something, and it's getting there. Looks like it's found about 8, so it's about an eighth of the way done, which means like a 16-minute runtime. And I don't know what kind of approach other people are going to be taking to this. Something that I do like is that the implementation is simple, so it's unlikely that I'm going to have spent all of this time and then end up with an answer that's wrong. But we'll see. I guess I could look at the problem statement again, give me actual. 216 extra index now produces your 64th one-time pad. Yep. Get it. Let's see. Could I? Yeah, I could, put the key that I'm on here, but I don't know if that helps. Yeah, let's see. So I guess another way to make this more efficient, like instead of using like regular expressions, we could, what we could do is, yeah, we could like iterate over the MD5 hashes, and then say like, so we could make a function like relevant subsequences of a hash value, and then say that it can either be the first pattern that matches, so like it can either be the first subsequence of 3 of a character, or it can be all subsequences, like all collections of all collections of 5 and the first collection of 3, and then maybe that would like collapse in a friendlier way. How far along are we now on the VPS? Oh, here we go. This is our number. Right answer, right? 38. Okay, so faster to the first answer and slower to the second. I wonder what approach other folks took. Maybe they're just on faster machines, which is completely legitimate. Yeah, let's go over the problem, I guess. So, well, first let's look at the leaderboard. Yesterday was an 80th. Today, 68. All right, making a little bit of a comeback here. All right, back to the problem. Okay, so this is basically a search to find the matching predicate problem, which we've seen a couple of before. So we're going to have a stream of strings. The stream is just generated by taking salt and then MD5ing. If we can close this, we already got the answer. So the stream is given by, let's see. Yeah, pretty straightforward. So here's how we get our stream. Basically take repeat our salt a bunch of times and then take 0, 1, 2, 3, 4, 5 all the way up. And then so this will give us a sequence of strings. And then this function isKey, which I guess I got pretty close to right on the first try. So that helped my time. But basically, so I originally was treating this like a predicate, and then I found out it's a little bit easier to make it actually return a value. So okay, so what we need to do is find the first instance in a string of all of it having three of the same character in a row. So here, what we're saying is break the string up into 3-character chunks. Filter apply. So find the first subsequence where every one of them is equal, and then take the first of the first. So the sequence that it returns is going to be the first of the sequence it's going to return is going to be, you know, three zeros, or, you know, 3 A's or whatever. And we just need one of them here. So bind this to the variable char, then repeat it 5 times, make a little string out of it, and then make a string that has the dot star in here. Then we can construct a pattern, and then construct like an anonymous function in here. Then what we do is we sort of specify that one of the things that you're going to have to provide into this function is the next 1,000 elements, and then in the implementation we are returning the index, and that's just because it makes things work nicer. So map indexed here, this is going to give us like 0 and the first MD5, 1 and the second MD5, and so on. And then what we're doing here is we are considering each of the each subsequence of 1001 MD5s, indexed MD5s, and then this is just some closure sequence destructuring. So isKey is going to get a collection as input. So that's the first layer of destructuring. The second layer up here is the first element is going to be a pair, the index and the hash, and then the second is going to be this next 1,000. And since each of these next 1,000s are also pairs, we have to make sure we map second to them like this. Then yeah, keep just is going to return. It keeps kind of like a combination of map and filter. It only returns those elements for which a non-nil value is returned, and then taking 64 of them. We could also, you know, if we wanted to like only get the right answer, then like, you know, last or something like that. But 64 is fine for observing our the output of our program. I did have one small bug in the beginning, which is that because I was originally using filter, it was returning this entire data structure, which meant that if let's say the, you know, some pair matched, then what would actually be returned would be something that looked like this, and so on, all the way up to 1,010. And then, so I was looking at the end of my program output, and I saw 1,010. I'm like, oh, okay, that must be it. But that's obviously wrong. What I actually want is this right here. So, so made that change, got the right answer, and got a few points. It was fun. Let's take a look at our admin calendar. All right, great. More color blue here. So I guess we'll see what that turns out to be. Okay. Um, next problem tomorrow night. Thanks for watching.